right. So first announcement is the that's weird. So do you guys see the engineering paper still, or did it switch back to the table?
Engineering paper.
That's weird because my little breakout window shows the table as well. I'm not sure why. Um, so quick announcements. The exam was scheduled for next week, and I will, based on your preferences, the people that are in the room right now, in the chat room right now, I am willing to do one of two things. The first would be just extend the due date, give you guys a week and a half, knowing that some of you have multiple exams next week. It's just where it falls on the syllabus. This would also happen if we were having face-to-face classes. It usually happens that we all kind of give our second exam around the same time, unfortunately for you. But because we're all online, it's really fine from my perspective to give you a week and a half for a due date. The other option is that I just move it back completely a week. Um, you would have a week deadline, and next week I would move forward to the next chapter, chapter 10. Chapter 10 would not be part of exam 2. So we would move forward in content, but the exam would still just be over the chapters that are established right now, which is through chapter 9. So if there's a preference between either of those options, I'm happy to do that. The revised syllabus I gave you said that just the exam was next week and that it would be due on Sunday. But having heard from a couple of you about all the other exams that you're taking, I'm happy to do either of those solutions to give you guys a little more buffer. Thoughts? Comments?
Use mini or anything.
Lily, what'd you say? Sorry, say it again.
We don't have to use Minitab yet for anything, right?
No, this one's still going to be all by hand. Exam 3 will be on Minitab, but you'll have access to it by then. And I didn't, usually I would include Minitab on exam 2, but because they're still working out the VPN and remote access to the computer labs and things like that for students. I've heard there have been some issues with that. And so I wanted to try to get those issues settled before I started making that a requirement.
Sounds good.
I know some of us are still waiting to hear back from Dr. Davis on when our modeling dynamic systems exam is.
Okay.
And so, honestly, my answer might depend on when that happens. But I mean, I would say I'm all for you extending it to a week and a half. That wouldn't be too bad in my opinion.
Okay. Thanks, Derek. Other thoughts?
I think the week and a half would be nice. I'd be afraid to push it back too much and then be like, oh yeah, that sounds great. But then we'll still have other projects and stuff to do. But a week and a half sounds good.
Okay.
Yeah.
So that sounds like the consensus. I mean, other people can jump in, but so far, sounds like just having the due date be a week and a half sounds like the right perspective. Sam agrees with a week and a half. So that is easy for me to do. So ignore the syllabus, the due dates, and I'll post it on Blackboard. The due dates will just be set up so that you have a week and a half. So we'll open this coming Monday at like 12:01 a.m. And then you'll have a week and a half to do that. So I think I have that planned for the following Wednesday, 11:59 p.m. The other thing that I was going to offer is I could send out a doodle survey on availability if Tuesday at 9 a.m. is not the right time to do the review, because that's what I was planning for next week, is that I would do a synchronous review, again showing the similar types of questions to what will be on the exam. If you went to the review for exam 1, you know that I tried to do basically one of every type of question that was going to be on the exam. So if you are interested in participating in that review session, I can just hold it Tuesday at 9 o'clock, like our normal class would have been. Or I could send out a doodle and we could do it at some other time, even Monday, to do it earlier in the week or in the afternoon if that works better for your schedule. Do people have thoughts on that? Is Tuesday at 9 just kind of already set aside that you have that time available? Is that going to work best? I see heads nodding from the people there on my screen. Anybody in chat want to chime in if Tuesday at 9 is still working best? Because then I won't bother doing a doodle survey. Dalton. That's good. Tuesday at 9 works. All right. All right. Okay, so we'll make the exam due date for a week and a half. We'll do the review as a synchronous Zoom on Tuesday and plan that it may be as long as an hour because I'll be doing one of every type of question and wanting to field questions from you as we go through. So plan that probably will be an hour. I'm not going to make it a super long exam. I'm really trying to give you equivalent to what we would do if we were in the classroom. And since our class is an hour and 15 minutes, I usually try to write an exam to be about 45 minutes for the average person. That gives a half-hour buffer for someone who wants to double and triple check all of their answers before they turn it in. So I try to write my exams to be about 45 minutes in length. So figure probably an hour to do the review for that. Does that sound okay for everybody? I'd also gotten a message, and I've heard this from some other faculty as well, because we do still have faculty meetings, kind of keeping tabs on how things are going. About some difficulty with Blackboard. I apologize, your material's getting up so late. I've had a lot of problems with Blackboard, and things just like I upload it and then there's an error and I have to go back and upload it again, or the access is wrong. I don't really think our Blackboard was meant to host the entire university online. And so it might just be exceeding its capabilities in a few ways. But I heard some other professors are creating YouTube channels and posting their videos to YouTube. So I've created a YouTube channel just called Dr. Ely, and that will have the videos. So I'll go back and upload the videos from the last few weeks, but then also be posting it there. So I think if everybody's okay with it, instead of posting the videos to Blackboard, I'm only going to post the YouTube link, because that should take care of the Blackboard upload issues, and you should still be able to stream it from your computer or your phone or whatever you watch YouTube on. Does that sound like that would work for everybody? Give me a head nod if you're on video, or type in the text box.
Sounds good.
Okay, that'll be my little pet project today, is getting that up and running. So that should take care of some of the lag. The last thing, and sorry there's so many announcements, last thing is someone let me know that there was an error in the quiz. I don't know how many of you have gone in and tried to take it yet, but it was identified that one of the questions had an error in it. Since the quiz has been deployed and at least one person has attempted it, the only thing I can do is throw out that question. So that's what I'm going to do. I'm just going to throw out that question. And so the quiz originally had 8 questions. It will now have 7. So I can go in and delete that question from the quiz and not disrupt any attempts that have already taken place. And it won't disrupt grading or anything. But if I were to revise it and fix that, then people who had already completed the quiz would be at a disadvantage. So it's kind of the only way to be fair for everyone across the board is just to throw away the question, and instead of the quiz being 80 points, 8 questions at 10 points each, it'll be 70 points, 7 questions at 10 points each. Does that make sense?
Where is that quiz actually at? Because it doesn't show up for me.
It doesn't show up for you. Anybody else not seeing it? Because I have it. I got to exit full screen here. Boy, I'm hard time finding it. I will send out the link. Yeah, I had someone else having a hard time finding it earlier. I don't know. Again, this is part of the Blackboard issue of I post things and I can see them and then you guys can't see them. It's been really difficult for me to make sure everybody's got all the same content. Anybody else who's on, like, have you seen in your Blackboard, do you guys, like, do you have visibility for the quiz?
Yeah, I can see mine.
I can see mine.
And it's just in that week of 330 folder. Julia can see it. Okay. Evan can see it. Okay. I'll go back and check on that, Zach, for you.
Which folder is it in?
The week of 330, March 30th. And it may be just like nestled in the middle. It says quiz chapter 8 and 9, I think is what it's called.
That's it now.
Okay, great. If you have not started it, don't start it. Let me go in and remove that question that's in error first. But I'll be doing that as soon as we end this. Like I said, I had a meeting right before this, so I hadn't had a chance to do it yet this morning. But I will go in as soon as we end this session and make the change to the quiz so that anybody who's wanting to jump on into their quiz is able to do that with that question removed. So, all right. I am now going to start the actual review, and we have 6 questions that we're looking at. It's going to feel pretty repetitive because this process is pretty repetitive. In fact, this is the same process that we're going to use as the basis for our statistical tests. And based on that, like I said, you'll be able to do the Z statistics and use all the tables and everything in your sleep, because it's so many of the tests are based on normal distributions that our setup and our hypothesis testing all kind of looks the same. So the first question, you are given a mu of 110, you're given a sigma of 5, and you're told to find the critical region based on a different alpha level and a different n. And so for our first problem, we were looking at alpha is equal to 0.01 and n is equal to 3. And so when we're looking to find our critical region, the first thing we want to do is we want to find the z of alpha over 2. And this is using the table, and for z of alpha over 2, we come up with 2.58. And so that z, again, that would be that z of 0.01 divided by 2. So that actually equals the z of 0.005. And you look that up in the table. And that's how you're going to get that z. So you should be able to go back and verify in your table that you have that. Now the critical region is going to be equal to the mean that has been given to us plus or minus that z alpha over 2 value multiplied by sigma divided by the square root of n. And if you remember, standard error is equal to sigma divided by the square root of n. So we're multiplied that standard error by our z of alpha over 2. And what is this doing visually? Well, this is giving us that region, that critical region on our normal distribution curve. So we've got mu in the middle, and then we're going to have a lower bound and an upper bound. And our z is telling us what percentage of the data is falling underneath the curve. So it's saying that your alpha over 2 is the tail and 99% is under the curve. That's what we're doing when we say 0.01 of alpha. That means your alpha over 2 is 0.005 on this side and 0.005 on this side. And so your question is, if mu is equal to 110, then the value of this lower bound is u minus z alpha over 2 sigma over square root of n. And your upper bound is mu plus z alpha over 2 sigma over square root of n. So I just want to write it out this way so that you have the visual. This is what you're looking at. And so the higher that z value is, the more of the curve that we're talking about. The smaller that alpha is, the more of that area under the curve that we're talking about, because the alpha is representing the tail. And so on a two-sided distribution, half the tail is on one side, half the tail is on the other side. And so the smaller that number becomes, the smaller these tails become, the wider that region becomes. And so all of those values are related to each other. And that's kind of the visual to keep that in mind. So the math is really easy, because the math is equal to 110 plus or minus 2.58 times, we have sigma was equal to 5, and the square root of n is square root of 3. So that's just from our given information there. And so our lower bound in this problem is equal to 102.55, less than or equal to mu is less than or equal to our upper bound of 117.45. And so this numerical expression, that would be, you could box that in, that would be the answer if that question was on the exam. That's the actual answer. But we're saying that there's a 99% chance that some sample mean is going to fall between these two values if your population mean is 110. And that's what that actually means. So part B, we're just going to change the alpha to 0.05, and we're going to change the n to 5. So since we have an alpha of 0.05, now we're looking at the area under the curve being 95. So draw that curve again. And so we're going to have our mean is still 110. But now we've got our upper and lower boundaries, upper, and we've got our tail is still representing that alpha over 2. But in this case, it's 95% in that center area, and that alpha over 2 is 0.025 on the upper side and 0.025 on the lower side. So what we've done is we've shrunk the area under the curve, right? We've shrunk the area that under the curve because now we're saying only 95% of the data points are going to fall in that area under the curve. And since 95% is less than 99%, we're looking at less opportunity for that mean, a lower probability. And so our lower bound and our upper bound are actually going to be smaller. So we can show that again by saying it's 110 plus or minus 1.96, because that's our z of alpha over 2. So z of alpha over 2 is equal to 1.96. So we've got that 110 plus or minus 1.96. And this time we have our same sigma that we had before, 5, but now our n is also 5. So it's 5 divided by the square root of 5. And so that means that our lower bound is 105.62, and our upper bound is 114.38. So again, you would box that in. That is your actual answer. And so this is a good problem because it's showing that at the 95% confidence interval, even though I changed n, I'm looking at a population whose mean is 110, and going to a 95% confidence interval instead of a 99% confidence interval, those lower and upper bounds are now inside. They're shorter than what it was for our 99%. So 99% was 102.55 to 117.45. 95% is 105.62 to 114.38, so it's narrower. There's some questions in your book that actually give you two different confidence levels and say one of these is 90, one of these is 95, which is which? And what it's looking for is that, you know, the one that's bigger is going to have a wider length than the one that's smaller, with all things being equal. So that's question one. Question two, everybody seeing on the document camera okay? Is this better than last time? This clear? I'm getting nods. Good. Good. I'm glad that that works. Okay. So number two, unfortunately, the document camera does not make my handwriting better. I don't think anything can do that at this point. Kind of old dog, new trick type thing. It's not going to happen. So our mean is 110. Our standard deviation is 5, just like it was before. And now we're going to say, you know, we're going to use that alpha equal to 0.01 and our n of 3. So it's going back to part A of question 1. But now we're going to actually find beta. And so the question is find beta given true mean is equal to 113. And so we're going to use our formula to find that beta, which is our type 2 error, and we'll be talking about that more. But finding our type 2 error, finding beta, means we use a formula that beta is equal to the probability that mu minus z alpha over 2, sigma over square root of n, is less than or equal to x bar is less than or equal to mu plus z alpha over 2, sigma over square root of n. Well, what did I just write? Well, I'm looking at the probability of a sample mean falling within the confidence intervals that we've established. But that confidence interval was based around the idea that we had a mean of 110, and we don't. We have a mean of 113. So it's based around faulty information. So remember what type 2 error is. Type 2 error means we accept it as correct even though it's false. So if I was looking at this from a quality standpoint, I would be saying type 2 error is the probability that I say a product works and I sell it to a customer, but the product itself is faulty. What's the likelihood that my sample mean is going to tell me to confirm my hypothesis, even though I'm wrong? So this type 2 error has you looking within the confidence interval, but you have to factor in the difference between the two means. And so in our textbook, we have a nice little symbol for this, a little squiggle symbol, which is equal to the mean that we actually have and the mean that we think we have. So the difference between those two means. And so if we want to find the type 2 error, the type 2 error is actually equal to the z statistic for z of alpha over 2 minus the difference between the two means times the square root of n over sigma minus the z statistic for negative z of alpha over 2 minus the difference between the two means multiplied by the square root of n over sigma. This is derived in your textbook. I am not deriving it completely here. It is derived in your book. So if you want to see the manipulation of the formula to get from here to here, look in your text. They do it step by step. So filling in our numbers, we knew that our z of alpha over 2 at 0.01 was equal to 2.58. So z of alpha over 2 is equal to 2.58. We looked that up in the earlier problem. That's the same z because we have the same alpha. So z of alpha over 2 is 2.58. So what I'm looking for is I'm looking at the z statistic of 2.58 minus 3, because that's the difference between the means. So this is equal to 113 minus 110, or 3. Times the square root of n, and our n in this case was 3, divided by sigma, which is 5. Minus the z statistic for negative 2.58 minus 3, the difference between the two means, square root of 3, because 3 is n, divided by sigma, which was 5. So this is equal to the z statistic for 1.541 minus the z statistic for negative 3.619. So I look these up on the table, and if I look up 1.54, that's 0.9382, and negative 3.619 is off my table, it's 0. So that is equal to 0.9382. Box that in, that's my final answer. So beta, or my type 2 error, is equal to 0.9382. All right. So the next problem is we're looking to find, we have some given information, and this is now in hypothesis testing, so we're going to actually write it out as a hypothesis. So we kind of reviewed our type 1 and type 2 errors. We looked at finding those critical regions, which is very helpful in doing hypothesis testing as well, and we'll do an example of that coming up here. So now we're going to be looking at calculating an alpha, calculating a beta, so our type 1 and type 2 error for a hypothesis test, and we'll also throw in calculating the power. And so our given information is that we're looking at a null hypothesis, and hopefully you've had a chance to watch the video, that for our hypothesis testing, our null hypothesis is looking at a given parameter. In almost all of our statistical tests, we're looking at a comparison of means. T-tests, ANOVAs, things like that, we're almost always looking at a comparison of means. We can also do hypothesis testing on the variance, and we can do hypothesis testing on proportions. And those are the three main ones that we're going to be working with in this class. So if I'm doing a hypothesis test on the variance, I'm looking at the chi-squared test. And if I'm looking at a hypothesis test on the proportions, I can do that as well. And we'll see how to do that in Minitab. So our null hypothesis, what I'm testing against, is I believe that the mean is equal to 175. Our alternative hypothesis is that the mean is greater than 175. We were given n is equal to 10, sigma is equal to 20. That's all given in the problem. The question is saying, part A is saying, find alpha when, for the probability that the mean is greater than 185, given that mu is equal 175. And I'm not sure if you remember this from algebra or even just when we did conditional probabilities, that line is kind of our given statement. So this is we read this as find the probability that x bar is greater than 185 given mu is equal to 175. So our given statement is given that null hypothesis. That's what we're testing against. So our given is always going to be that null hypothesis. Our testing is looking that x bar is greater than 185. And so to do that, we are going to do the probability that x bar minus mu divided by sigma over square root of n is greater than 185. And so what we're actually calculating, that z statistic, is the probability of 185, because that's the x bar that we're given, minus 175, because that's the mu that we were given, divided by 20, our standard deviation, which is divided by the square root of 10, or the given n, because we're looking at our z statistic, and so this boils down to 1.58. And so to find alpha, you are looking at the probability that z is greater than 1.58. However, the z-table is based on the left-hand side of the curve. So this is actually equal to 1 minus the probability that z is less than or equal to 1.58. So I look up 1.58 in my table, my z-table, and I find that I'm looking at 1 minus 0.9429. And 1 minus 0.9429 is equal to 0.0571, or 5.71%. So I could build a confidence interval against this mean now, a one-directional confidence interval where alpha is 5.71%. It's kind of a weird number to base an alpha on. Usually we would do just 5%, 0.05, not 0.0571. But basically what we're looking at is a 95% confidence interval for a one-direction hypothesis. So if I wanted to build the confidence interval off of that alpha, I could. But the question doesn't actually ask to do that. The question asks to find your beta type 2 error if the mean is actually 185. So if your mean is not 175 as you hypothesized, but it's actually 185, what is that type 2 error? Well, I'm looking at the probability of x bar minus 185 divided by sigma over square root of n, which is actually equal to 185 minus 185 divided by 20 over the square root of 10. So I'm looking at the probability that z is less than or equal to 0. Now I could look that up on my table, but hopefully you all know that 0 is 50%. It's right in the middle. So if my true hypothesis, if my true mean is 185, but my hypothesized mean is 175, I'm going to admit an X bar sample. I'm going to confirm that and accept my hypothesis half the time. And that means the power of this test is equal to 1 minus beta, which is equal to 1 minus 0.5, which is equal to 0.5. So that's telling us, based on our current sample size, based on our current hypothesized mean, based on the data that we have right now, we're getting it wrong half the time. It's not a great test. need to look at increasing our sample size or decreasing our standard deviation, but our data is not good here because half the time we're confirming a false hypothesis. So we are accepting something that we should have rejected. That's what that power is telling us. How often are we accepting something we should have rejected? Half the time. That's not great. Okay, so most of the questions here and in your homework and on the exam, are all focused on this idea of kind of manipulating. For chapter 9, it's kind of manipulating these formulas. So given one thing, find something else. And the reason that we're doing that is because when you do hypothesis testing in Minitab, you're going to input these numbers into the computer and then you're done. Like you're going to input these numbers into the computer and it's going to spit back a p-value. You need to understand what that p-value is. You need to understand how the z relates to it. You need to understand, because the point of statistics is to make a decision. You're comparing things, you're testing things, you're trying to figure out if something is good. If I'm working for NASA and I'm looking at likelihood of their life support failing given a certain situation, do I want to accept bad data half the time? No. If I'm looking at using a certain propellant to blow open an emergency life raft on an airplane so that if it crashes, the wings come down and these life rafts automatically inflate into slides and detach to be floatable devices. Like, I'm looking for something like that. Do I want to accept a product that half the time is wrong, but because of my testing, I'm accepting it as correct? No, that's terrible. So statistics is about decision making. So these numbers matter. Now, from your case, you're answering a question on a quiz or a homework or an exam. It's just data. It doesn't actually mean anything to you. But when you're using statistics in an engineering position, you're making a decision of that. You're basing your recommendation to your boss or to your client on your understanding of statistics. And so this class is really critical in making sure that you keep people safe and that you do your job well. So I want you to understand why these things are the way they are, because once you start working in Minitab, you literally click on a dialog box, enter like 3 numbers and hit OK, and it spits out the answer for you. But if you don't know what to do with that answer, or you don't know what that answer means, people's lives could be at risk. So it's important that we actually get why things are the way they are from a statistical standpoint and what the numbers mean. So the next problem, we're going to be finding an alpha given an acceptance region. So instead of being given the alpha, we're given that our null hypothesis is that mu is equal to 5. It's a two-sided test because my alternative hypothesis is mu does not equal 5. So instead of looking at greater than or less than, which is just a one-sided test, I'm looking at a two-sided test because I'm looking at either mu is equal to 5 or it isn't. My sample size given to me is 10, and my standard deviation given to me is 0.3. I'm being told an acceptance region, and we talked a little bit about this last time, is that oftentimes in manufacturing, your acceptance criteria or your acceptance region is where you start, because you have tolerances associated with your process or your product. And you know that that's a 4.85. Sorry, I kind of wrote that sloppily. It's 4.85 is less than or equal to x bar, which is less than or equal to 5.15. So the mean is supposed to be 5. We're giving ourselves 0.15 leeway on either side, right? So if something is 5.05, I'd accept it. If something is 4.75, I'd reject it. Does that make sense? anything within 4.85 and 5.15, I'm going to accept. Those are like our tolerances. The actual statistic, the actual mean is 5, but I'm going to give myself 0.15 buffer on either end for my acceptance criteria. So I'm going to find what that alpha is that gives me this acceptance range that I want. So knowing the range of values I want to accept, what is the alpha equal to? That's what this question is asking. So my to do this graphically, because I just want to make sure the image is there. If my mu is equal to 5 and my lower bound is 4.85 and my upper bound is 5.15, then I have an alpha over 2 for both of these tails, and I have a percent that's in the acceptance region. But I don't know what those are. That's what I'm finding. I'm trying to find that alpha. So I know what the lower and upper bounds are, but now I want to find the alpha that gives me that acceptance criteria. So that is equal to the probability that x is below 4.85 given that the mean is equal to 5, plus the probability that x bar is greater than 5.15 given mu is equal to 5. Why is that true? Well, I'm looking for my alphas over 2. So I'm saying how many times is my x bar going to be in this alpha over 2 region up here, and add that to the number of times that my x bar is going to be in this alpha over 2 region down below. So this formula directly corresponds to this graphic here. This probability is related to that section of the graph. This probability is related to this section in the graph. And this center section is what I'm actually going to accept for my x bars. So that's what this question is asking for. The rest is math. So probability that z is less than, because I'm calculating a z statistic, 4.85 minus 5 divided by 0.3 over the square root of 10. So this is my little formula that you should be seeing in your sleep. X bar minus mu divided by sigma over the square root of n. So that's my z statistic, plus the probability that z is greater than 5.15 minus 5 divided by 0.3 over the square root of 10. Now these two are going to be symmetrical. Why? Because my z chart is symmetrical. Could you have an acceptance criteria that is skewed and is asymmetrical? Yes. Yes, you could. The manufacturer could choose that. It doesn't happen often. Most of the time, we're going to see that it's symmetrical. So we have the probability that z is less than negative 1.56 plus 1 minus the probability that z is less than positive 1.56. Why did I have to do that? Because my z greater than means that I have to do 1 minus z less than. So this mathematically equals 2 times 1 minus the probability that z is less than 1.56. Or remember our formula that our p-value is equal to 2 times 1 minus the z statistic of z naught. That p-value formula is in your textbook. Well, we've just kind of derived it here. So I wanted to do this problem because it gives you an idea to actually see how you get from this acceptance criteria to this p-value calculation step by step. And so this is what we're asking for. This is what it relates to in probability. This is what it relates to with your z statistic. That converts into this singular formula, which its general form is written here. So we've just kind of derived that whole process.
Why is that 1 multiplied by the 2 also?
Because I have the probability that z is less than or equal to 1.56 and the probability that z is less than or equal to 1.56. That one's negative and that one's positive, but it's symmetrical, right? It's symmetrical against the mean. So those values are the same. So I can do 1 minus the probability that z is less than 1.56. I can ignore that sign because it's symmetrical. So I have 2 of them. So 2 times 1 minus that probability. Because 1 minus this probability is going to be the same number I have as the probability here. So I'm doubling it, or 2 times that. Does that make sense, Derek?
Yeah, thank you.
So this is the general form, and that's why I wanted to derive it, because the general form is the z statistic for the absolute value. And that's why we have these absolute value signs here. And we can do that because the normal distribution is symmetrical against the mean. Not every distribution is symmetrical against the mean. The exponential is not. The Poisson is not. We can only do this because the normal distribution is symmetrical against the mean. All right, so now we just plug in the numbers. So 2 times 1 minus 0.9406 is equal to 0.1188. And that's your actual answer. That's the alpha. You can also write alpha is equal to 11.88%. I will say on the quiz, put all of your answers in decimal form, not percentages forms. So it says it on the instructions of the quiz, but please make note of that as well, that all of your answers should be decimal points, not percentages. Blackboard will mark you wrong. And I have put in a tolerance on Blackboard for those fill-in answers that are self-graded, so that if your rounding is different, that it shouldn't mark you wrong. I've given you some wiggle room in each of those answers so that even if you round differently than I rounded, that you would get the same answer, or that it would be marked correctly. So, but make sure you're putting it in decimal form, not in percent form. Any other questions on this problem? Like I said, I specifically wanted to do this problem to walk through how all of these are related to each other, because that p-value is our focus of all hypothesis testing. It is all about the p-value. And so that's why I want to make sure that we're confident of what is the p-value representing. The p-value is representing how much of our data falls outside of our acceptance criteria. So what does that mean? Generally speaking, we want a small p-value, right? Generally speaking, we want most of our data under the curve. We want it within the acceptance region. We want this area to be small. All right. Question number 5. So in this case, we're gonna do a couple calculations here. We're given that the null hypothesis is mu is equal to 35, and the alternative hypothesis is that mu is not equal to 35. That means, again, we've got a two-sided. If it's greater than or less than, we've got a one-sided. But if it's equal, not equal, it's two-sided. Our n is equal to 10. Our sigma is 1.8. And our sample mean was 35.71. So we're tasked with finding the p-value, and we do that by finding our z statistic. So we're going to start by finding our z statistic. And so that is the difference between x bar minus mu divided by sigma over the square root of n, just like we've been doing all along. So that's 35.71 minus 35 divided by 1.8 over the square root of 10. And that is equal to 1.247. So now that I have that z value, I can quickly find my p. My p value is equal to 2 times 1 minus the z statistic, the absolute value of that z statistic. This is for two-sided hypothesis test. We'll do a one-sided in just a second, but this is for two-sided. So in this case, I look it up on the table and I've got 2 times 1 minus 0.8944, which is equal to 0.2123. Blending my parentheses and brackets, aren't I? So part B says, well, let's set up a 95% confidence interval. So ignoring what I did in step 1, I'm going to use the z of alpha over 2 for a 95% CI. And the z for alpha over 2 for a 95% ZI is 1.96. So I have my confidence interval is going to be equal to the sample mean plus or minus the z of alpha over 2 sigma over square root of n. And so that equals 35.71 plus or minus 1.96, 1.8 over the square root of 10. And so working out that math, now based on this sample, would we accept the null hypothesis? Answers, anybody? Anybody on mic or chat box or something? Would we accept the null hypothesis? The null hypothesis, remember, mu is equal to 35. Yes. Yes, Libby, you are correct. You should accept the null hypothesis because the null hypothesis is within this bound. 35 is between 34.594 and 36.826. So when we do hypothesis testing, we can confirm, we can do it against p-values, but we can also do it against the confidence intervals, the acceptance criteria. And so we're going to practice this a lot in chapter 10 as well. You're going to see this a lot in chapter 10, that we're comparing p-values for our hypothesis test, or we're using the confidence intervals. And so this is just an example that if I'm constructing a 95% confidence interval against that mean, is my hypothesis accepted, Yes, it is. And I can say that my hypothesis of mu is equal to 35 is accepted because it falls between the lower and upper bound of my acceptance criteria. So the last part of this question was just looking at the difference in calculating a p-value against a one-sided hypothesis. So what if your null hypothesis is that mu is greater than 35? What would my p-value be then? Well, my p-value for one-sided, for a greater than, is going to be equal to 1 minus the z-statistic, 1 minus the z-statistic against that mean. Now, if I was doing an alternative hypothesis for less than, my p-value would just be equal to the probability of that z-statistic, right? So that's in that box that's in the lecture notes, but my p-value for a mu is less than is going to just be equal to the z-statistic. But if I'm looking at greater than, I have to do 1 minus because, again, my table is always looking at the left-hand side of the curve. So this is equal to 1 minus 35.71 minus 35 divided by 1.8 over the square root of 10. So the z-statistic remains the same. We just used it above, but we're going to use it again. And so that same probability that we came up with holds. So that is equal to 1 minus the z-statistic for 1.25 is equal to 1 minus 0.8944, which is equal to 0.1056. Okay. So the last thing we're going to do today, the last problem, is looking at what if we are using the t-distribution instead. So make sure for your quiz and your homework you have both your z-table and your t-table out. You can either use the PDFs posted or those that are in the back of your book. And so the only thing that changes when we're looking at this is that this problem is, can you hold on 1 second? I'm going to pause this just to shout at my husband to close the sliding door. David! David! Sorry about that. The yard people are doing all the work outside, and I don't know if you could hear it, but I couldn't hear anything. Okay, so we're going to be using the t-distribution instead, and the t-distribution is means that we have a way of handling things that are normally distributed, but an unknown variance or unknown standard deviation. And so we're going to use the sample variance or standard deviation instead. And so if I have a n greater than 40, I can just assume that my sample standard deviation is close enough to the population that I can just go ahead and use the normal table. But if my sample is less than 40 and I don't have a population variance, which is going to be most of the time, remember, most of the time in reality, we're going to be using t-tests because we're going to have small sample sizes and we don't know the true population variance. We have to use what we found from our sample. And so in this case, we're going to be given that the sample mean was calculated to be 524.6, and the sample standard deviation is equal to 27.6821. Our n is only 5. And we're going to look at an alpha of 0.05. And we're going to test the hypothesis that the actual population mean is equal to 550 against the alternative hypothesis that mu is not equal to 550. So we've got a two-sided test, and we're looking to see whether or not we should accept or reject our hypothesis based on that sample. So what we're being asked here is, we want to know, can we say that the population mean is 550? This is the sample that we took. We took a sample of 5 data points. We calculated their average. We calculated their standard deviation. We want to be able to say that with 95% confidence. So that alpha of 0.05 means that we have a confidence of 95%. So we want to say, are 95% sure, based on this sample mean, that our true hypothesis is 550? Can we say that? Well, what's our rejection criteria going to be? And this goes back to that 7-step hypothesis method we talked about in lecture. We're going to reject the null hypothesis if the absolute value of our t-statistic, and again, we can use the absolute value here because the t distribution, just like the z distribution, is symmetrical on the mean. So if t naught is greater than the t alpha over 2 n minus 1, because that's for our t distribution, two-sided means alpha over 2, n minus 1 is our degrees of freedom, as we talked about last week. So we can actually calculate our t-statistic, and we're going to compare the absolute value of our t-statistic to our t-table for that given alpha of 0.05. So the first thing I want to do is I'm going to look up this t-value. So if I have a t of 0.05 divided by 2, and my n minus 1 is 5 minus 1. What I'm looking up on the table is t 0.025 and 4. So this right here is what I look up on the actual table. That value is equal to 2.776. So what did I say? I said my criteria is to reject the null hypothesis if the absolute value of my test statistic, my t-statistic, is greater than 2.776. So that's what I'm going to be looking at. Is t naught greater than 2.776? That's my question. That's how I know whether to accept or reject. So, to calculate my t-statistic, I'm going to use the same formula that we know and love, and that's our x bar minus mu over the sample standard deviation divided by the square root of n. And so that's equal to 524.6 minus 550 divided by 27.6821 divided by the square root of 5. And that gives us a t-statistic of negative 2.05. Now, I use the absolute value. I'm going to write that down again. I use the absolute value. So is 2.05 greater than 2.776? No. So I'm not going to reject it, or I'm going to accept the null hypothesis. So going over the hypothesis testing, again, we write out our given information, we write out our null hypothesis, our alternative hypothesis, We determine what our rejection criteria is going to be, and for a t-distribution, we're going to reject the null hypothesis if the absolute value of the test statistic is greater than the t for that given alpha. We look up the actual alpha level, and so that's t of 0.05 over 2, comma, n minus 1, which is equal to 2.776 in this case. And so then we're going to create our test statistic and calculate that and compare it to that 2.776. And if that 2.05 was greater than 2.776, then we would reject. But because it is not bigger than 2.776, we do not reject, or in other words, we accept the whole null hypothesis. Now we're going to do this again, but this time we're going to do it as an acceptance criteria. So I think the question said, confirm your answer using acceptance criteria. So 6B. Again, our X bar, I'm just going to rewrite it since I started a new page here. Standard deviation 27.6821, n is equal to 5. Confidence level is 0.05. Null hypothesis was mu is equal to 550. Alternative hypothesis is mu is not equal to 550. So if I wanted to build a confidence interval, the first thing I would do is I would look up t of alpha over 2 n minus 1, and that is equal to, in this case, t of 0.025 comma 4. And so it's that same value we wrote down before, 2.776. And now I can build my confidence interval as x bar minus t alpha over 2 n minus 1 times sample standard deviation divided by square root of n less than or equal to mu is less than or equal to x bar plus our t statistic times the sample standard deviation over the square root of n. So that's our normal formula for creating a confidence interval using a t-distribution. That's what we learned last week. And so now I'm going to use this to test my hypothesis. And so what I find is that I have 5.524.6 minus 2.776 multiplied by 27.6821 divided by the square root of 5 less than or equal to mu is less than or equal to 524.6 plus 2.776 times 27.6821 over the square root of 5. And I crunch that math, and I get 490.23 is less than or equal to mu is less than or equal to 558.97. So, do I accept a null hypothesis that mu is equal to 550? Well, yes, I do. Because 550 is between the upper and lower limit of that confidence interval. So I just calculated a p-value to test the hypothesis, and I used a confidence interval to test the hypothesis. To do the p-value, I have to calculate the t-test statistic. To do the confidence interval, I have to calculate the upper and lower limit. Both of them mathematically are going to always give you the same answer, either accept or reject. If one is accepting it, then the other would also accept it. If one is rejecting it, the other would also reject it. You can use these methods interchangeably. unless the assignment says you have to use the confidence interval method or you have to use the p-value. If it tells you that you have to use one or the other, that's fine. But if it doesn't tell you, if it just says, do you accept or reject the null hypothesis, you can use either method, p-value or creating a confidence interval. And that's true for the z distribution as well. When you're doing hypothesis testing on the z distribution, your normal distribution, again, you can either calculate your z statistic and look at your p-value, or you can calculate a confidence interval and look at your hypothesized mean and see if it falls within the upper and lower limits of your confidence interval. Both methods are equivalent. Does that make sense? All right, so what I'm going to do, I'm going to post this to YouTube, and I will post up the YouTube link. I am going to go in and fix the quiz. I'm going to delete that question that had a typo so that everybody has an equal share. The exam is going to be scheduled for a week and a half for you to get that done. There will be no Minitab usage. It's all going to be a written exam, and you will need to show your work. If you have Minitab or Excel and know how to use it to answer these questions, you still have to show your work. So you're still going to have to physically write out the process of how you get from point A to point B for your answer. If you have those resources at home and want to check your math, that's okay. I mean, obviously, you have that resource. It's a take-home exam. I'm not using Proctorio. It's not going to have a set start and end. It's going to be a PDF that you can download and work with, and you'll upload a handwritten or typewritten response. But I'm not going to mess with Proctorio, and I'm not going to mess with having a certain time interval other than just saying that it's due at a certain time. So you'll be able to chip away at it a little each day if you want, however you want to approach that. And we will do a review session on Tuesday at 9:15. Sound good to everybody? Are there any other points of order? I think I hit all the comments that I had been getting.
I just wanted to double check for our quiz on Sunday, if we're allowed to use notes or not.
Oh yeah, yeah.
Yeah.
I mean,
Okay.
anything
Okay.
here is you can use it. It's take home at this point.
Okay. That'd be super.
Yeah, that's why the homework and the exams, I'm really looking to see you show your work. That's what's showing me whether or not you know the stuff. If we were in a classroom, I actually have a formula packet that I would provide. You wouldn't be allowed to use any notes. You'd have an hour and 15 minutes to get it done. That's not the situation we're in anymore. So we're just going to go ahead and focus on that instead.
Thank you.
So did it work? Do you guys see me now? Oh, okay. Because I've got a window that's showing my table for some reason, and my window. I don't know which camera that is, but something somewhere is showing my table. So that's weird. Anyway, stay safe, stay well, stay at home. And hopefully, if you have any questions or any other comments, I'm trying to respond to them as quickly as I can. I've got 4 different classes that I'm juggling, but I know that you guys are all juggling 5 or 6 or 7 classes as well. So we're all in this together. Just be patient with me. I'll be patient with you. And if you're having any other tech issues, let me know. I have my sons helping me with the YouTube thing, so that should work out okay because they know how to do all that. They stream all their video game content, so they're used to doing that. So, all right, I will see you guys Tuesday. Have a great day.